Okay, so here's the solution for test 5. So for problem number 1, we had this product rule. So I called f of x the natural log of 3x and g of x 2x cubed minus 4x. So you take the derivative. A lot of people forgot this extra 3, so it's 1 over u times u prime. So u prime is 3. So you can cancel out the 3's and you get 1 over x. The other way you could have done it is actually broken this down into the natural log of 3 plus the natural log of x. When you take the derivative of the natural log of 3, you get 0. So either way, nobody did it the second way that I told you about. So you get f prime of x times g of x plus f of x times g prime of x. Each one of these terms here in this square bracket has a factor of x, so you can simplify it down to 2x squared minus 4. So fair amount if you forgot to see that simplification. Okay, number 2, chain rule. So u is the quantity in the parentheses. So if we write this as our normal chain rule thing, f of u is 3 over u cubed, which can be rewritten as 3 times u to the minus 3 power. And use the power rule, so you subtract 1 from the exponent, multiply by the exponent. So 3 times negative 3 is negative 9. And then ultimately you have to rewrite this as u to the 1 over u to the positive 4 power. I ended up doing that here instead of here. So the derivative of e to the 2x plus x, well, the derivative of x is 1. The derivative of e to the 2x is 2e to the 2x. So you actually had to use the chain rule here as well. But, it's kind of like the sine of 2x. You get 2 cosine of, so same thing applies. The derivative of this is multiplied by that. So it's not really necessary to go through the whole chain rule for a simple expression like that. So a lot of people forgot the 2. So f prime of x equals f prime of u times u prime of x. So this is f prime of x, f prime of u, this is u prime of x. And then you plug u back in. I move this to the denominator to make the exponent positive. You can also see the points, 20, 20, 20, most of them are 20. This is where you're taking the integral of a to the u du. So it's not e, it's 3. So u is the exponent. So you take the derivative of that, you get 9x squared plus your dx term. We have x squared dx. X squared dx is du over 9. So for this and that, we get du over 9. 3 to the u, factor out the 9, and then the integral of a to the u is 1 over the natural log of a times a to the u. The 9 here is right there. Okay. And then you plug u back in. Notice I'm adding my arbitrary constant c here immediately afterwards. The integration, that was that one. Next one, using the properties of logarithms. Most people did pretty good on this. Much better on this, remembering the x part. A lot of people used to forget that, so I guess I emphasized that well. The biggest error was people forgot to subtract this term because it's in the denominator, so a lot of people had plus 2. Here, you could either take the derivative of this or you could take the derivative of that. So what I did here is I took the exponent out. So you get 2 times the derivative of the natural log, which is 1 over x. Or the other way of doing it, which most people did it this way, but a lot of people messed up, was they did 1 over x squared. But remember, it's u prime over u, so it's 2x over x squared when you take the derivative of this, which simplifies down to 2 over x, which is the same thing I got up here, because this cancels out with one of those. And if you plug in x equals 1 from here, you get 2 over 1, which is 2. So that's from your slope, your point, your final answer. So this one's like problem 4, except you have to use logarithmic differentiation, which means you have to take the logarithm of both sides. Then you can use the properties of logarithms to expand this out, which gives you this. Again, a fair number of you forgot this was in the denominator. So you have plus, but it should be negative. Another issue, a lot of people forgot that the derivative of 2x minus 3 is 2. You just put 1 over that. So you miss that factor of 2. So once you take the derivative of both sides, you've got to show your implicit differentiation over here. You need to solve for y prime, so you multiply both sides by y, and then you plug y back in, and you have this final result. I said you didn't have to simplify it. Okay, next one, most everybody got right. So it's just the chain rule. F of u is the natural log of u. U of x is 3x squared minus 3x to the fourth minus 2x. Here's the derivative. So it's u prime over u, or you can take f prime of u times u prime of x. I use the more traditional way here. So there's your answer. Next one, I said, find the indefinite integral using completing square in the denominator to fit the appropriate integral. So this doesn't fit anything, but u squared plus a squared fits the arctangent. So you take the denominator and you add 9, subtract 9. So you take half of 6, which is 3, squared, which is 9. So you add 9, subtract 9. So these three terms can be rewritten as a complete square. 58 minus 9 is 49. So the original integral becomes this one. So u is x plus 3. A is 7, square root of 49. Du equals dx. So this then becomes this. I factor out 7. The integral of 1 over u squared plus a squared du is 1 over a arctangent of u over a. And then you plug u and a back in. So 1 over 7 cancels out with this 7. And you have x plus 3 over 7. Some people picked a as x plus 3 and u is 7, and that does not work. The u always has to involve the x term. I know why you did it, because it's a squared plus u squared, so you thought this was a squared. This was u squared, but the u always involves the variable. Okay, the next one. So not many people got this completely right. So I'll go through this a little slower. This was worth 30 points. Yeah, some of these others were worth 10, I think. This one was worth 10. Okay, so I told you this involved the inverse, the arcsecant. So if you use something other than the arcsecant, then you weren't listening to me. So this, if you look at the arcsecant expression, you have u squared minus a squared. So u squared is 5x squared. So when you take the square root, you get the square root of 5x. Some people still have the square root of 5x squared, but the square root of x squared is x, being to take the separate. A squared is 6, so a is the square root of 6. So when you take the derivative here to get du, you get the square root of 5 dx, or dx is du divided by the square root of 5. You also have to change the limits from 2 to 3. So you plug x into here, so you get 5 square root of 5 times 2 and the square root of 5 times 3. Or the other way around, 2 square root of 5, 3 square root of 5. So those are my limits. So you can see I can make these substitutions. The 4 I bring out. 2 becomes 2 square root of 5. 3 becomes 3 square root of 5. X becomes u divided by the square root of 5. So that's down here. X is u divided by the square root of 5. So that's, a lot of people didn't get that extra square root of 5 in there. 5x squared is u squared. Negative 6, or 6 is a squared. And dx is du divided by the square root of 5. Well, these two cancel out. Some of you left both of them out, but you get points taken off because you didn't make the right substitutions, even though you might have gotten the right answer. So these square roots cancel out. So it becomes this, which is exactly what we're looking for if you look in the book. And the integral of this is 1 over a arcsecant the absolute value of a over a times 4 with these limits. Plug in the upper limit, plug in a, subtract the lower limit, and you get the answer 0.336. Notice here, you guys must have arcsecant somewhere in your calculator because I didn't see many people who actually did this, so maybe I need to look that up. No, it's probably too late for me to do that, but you can see how I switch the numerator, the denominators to get the value. Okay, the next one was easier because it was almost in the right form to start with. So you got a squared minus u squared. U is x, a is 5, du is dx. The limits the limits change because they go from x to u, but the numerical values don't change. So if you make these substitutions and factor out the 3, you get 1 over the square root of a squared minus u squared du, which is the arcsine of u over a. Plug in the upper limit, subtract plugging in the lower limit, and you get 1.55. Most everybody got this right. There were a couple of people that kind of combined the two methods. They ended up including 6x squared twice. So you either use one method or use the other. One method is, so just make sure you don't double dip here when taking these derivatives. So this is the derivative of the arcsine of u is u prime, but u prime is just 1 if you're taking the derivative with respect to u, so it's not u prime again. So hopefully you'll see why you're not supposed to do that twice. So you just have 6x squared one time. And then you have square root of 1 minus u squared. U squared is what's in the expression here, and I didn't ask you to simplify it. The final one, this was something I added at the end to your test, but here it is. So I said to break this up into 2 parts. So you've got one part where you've got the entire denominator as originally written. Then you've got the denominator rewritten in a complete square form. So here's the complete square. So you take half of 6, which is 3, squared, which is 9. You add 9, subtract 9. Some people added 9 twice. Subtract 9. So you get 26 here. So you've got these two denominators. They're the same, but they're set up because this one's going to involve the natural log, and this one's going to involve the arctangent. So 7x minus 15 has to equal a times the derivative of this denominator, which is 2x plus 6, plus the b, which goes with the second grouping. You multiply it all out, set the coefficients of the x's equal to each other. 7 equals 2a, and then the constant parts, negative 15 equals 6a plus b. From this one, you can calculate a, plug a into here to solve for b. So you get a is 7 halves, and b is negative 36. And that's the final answer I was looking for. Now, on the final, I would ask you, I put in one with a definite integral. So you'd have to go through this whole additional process. Here u would be equal to x squared plus 6x plus 25. Here u is equal to x plus 3, and a is equal to the square root of 26. Du equals dx. Here du equals 2x plus 6 dx. So then you'd have 7/2 the integral, and you'd also have to do, change the limits when x equals something, u equals. So you have to get the u limits. But here you'd have 1 over u du. So this would end up being the natural log of u evaluated between the limits. And over here you'd have 36 times 1 over u squared plus a squared du. So the answer would be 1 over a arctangent of u over a evaluated between the u limits. And u here would be, let me just put some numbers in here, say 1 and 2. So here u would be equal to 1 plus 6 plus 25, which would be 32. And here u would be 4 plus 12, which is 16. 16 plus, that'd be 41, I think. 4 plus 12, 16, 16. Yeah, okay. So those would be the u limits. So you'd have 32 and 41, 32 and 41. Over here, when x equals 1, u would equal 4, and when x equals 2, u would be equal to 7, right? Is that right? No. 5. Okay. So these would be from 4 to 5. So when you actually evaluate this, you'd have the natural log of the absolute value of 41 minus the natural log of the absolute value of 32. So that would be this one. And here you'd have 1 over a. A is the square root of 26. Arctangent of u, which is going to be, so we're not plugging back in, we're using our new limits. And then you get some answer there. So I've worked it through with some numbers substituted in, but for this problem, that is what I was looking for on the test.